Welcome back. Let's wrap up with binary heaps by talking about how they perform, their big O notation, mainly for time complexity. So binary heaps, both min and max heaps, are great when we're talking about insertion and deletion. That's really what they excel at. They're very fast. Big O of log n for time complexity. So remember, from a binary search tree, that is very quick when we compare it to all the other sort of standard big O's that we've seen. So all the way down here in this sort of light green, not the dark green, but the light green. So as n grows, the amount of time that it takes to insert or to remove something from a binary heap grows slower. It grows at the rate of log n approximately. So let's talk about why that is. So first, remember when we say log n, it's actually log base 2 of n is what it's really referring to, although that doesn't actually matter because we're just kind of referring to this general trend. But if we think about it that way, when we talk about a binary heap, we're talking about log base 2 of n. Well, each time we go down a step in a binary heap, or just any binary tree structure, we have 2 times the number of nodes. So we have 1 node, then 2, then 4, then 16, and so on. So let's focus on insertion. If we want to insert the number 200 into this heap, worst case, which we know is true actually because it's the largest number, it's going to end up over here. But along the way, we only have to compare it 1 time per row, right? 1 time per level of this heap. So we compare it to the first parent, which is 9, because remember, everything's inserted on the left. So 200 is going to be a child of this 9 element. So we compare it, that's 1 comparison. We compare it to its parent, 2 comparisons. Again, 3 comparisons, and then the 4th comparison. And then at this point, we realize, okay, well, 200 is the largest element. If this is a max binary heap, it needs to be the root. So that's 4 comparisons. So for 16 elements, we're talking about 4 comparisons. So you can think of it as 2 to what power gives us 16. 2 to the 4th power, 2 times 2 times 2 times 2 gives us 16. Or if we were to hop over here, this is a maxed out. Unfortunately, I actually can't insert anything else into this heap. The limit is 31 nodes. But if we were to insert something right here, this is where it would go next, to be the 32nd node, we would, if it was, let's say we insert 100, which is larger than the root, to find its way up here, it's 1 comparison, 2 comparisons, 3, 4, and then 5 comparisons. So for 32 nodes, we're talking about 5 comparisons, 5 operations. So as n grows to 32, we think about 2 to what power gives us 32? 2 to the 5th power. 2 times 2 times 2 times 2 times 2. So another way of putting that is every time we double the number of nodes, every new full complete layer, we are only increasing the time that it takes by 1. So when we get to 64 nodes, we're talking about 6 operations. And hopefully you can see why it'd be the same for removal, because we insert at the or we remove from the beginning, we swap something to be the new root, and then we have to compare. And if it has to sift all the way back down, the max number of comparisons is going to be the same as we saw here. It's log n. It's the same idea between insertion and removal. Now you might remember from when we talked about binary search trees, where they also had a log n insertion time. In general, or an average / best case, there was also a worst case scenario. Remember this? The very depressing tree that really doesn't look much like a tree, sort of looks like something else. The big O, time complexity, to insert into this tree or to search is O of n because of the way that it's set up, right? If it's constantly just dot right, dot right, dot right, dot right, it's going to take, however many nodes are in here. That's potentially how long it would take to insert if we were trying to insert 100 or something. This is not a problem when we're talking about heaps. Now, why is that? Well, heaps can never look like this. This is against the rules of a heap. Remember that when we insert into a heap, we always fill out the left side first. So unlike a binary search tree where we might have, an incomplete row, well, I shouldn't call it a row, an incomplete level, instead, everything is always filled out before we move on to the next level. So this entire row, this entire section is done, and then we start inserting here and here, and then we keep going across. So there is no possibility for us to have such a crazy, unbalanced, unhinged, depressing tree. And because of that, worst case is still O of, all the way back here, log n for insertion and removal. Now, binary heaps are not really made to to be searchable. Like if you really care about optimizing your search, then you probably want to use a binary search tree or something like that. So time complexity for search is O of n. Remember that when we look at a binary heap like this, there is no guaranteed order or even an implied order between siblings. So if we're searching for the node that contains the value 1, if we start at the beginning, well, we can't make a decision. We can't, with a binary search tree, we could say, all right, well, it's less than 86, so it's somewhere over here. That's not the case here. It could be anywhere because 1 is less than 86. It's the only condition that we know for sure is true about all of these nodes is they're less than 86. So then we have to look over here and, well, once again, we can't really make a decision. It's somewhere down here maybe, but it still could be over here. And so we keep going and, we're going to have to search here and here and here and here. And finally, we'd find 1. But it also could be over here. There's no rule that it has to be here. It's just in this given scenario, it is. Now, that is a bit of a worst case. Now, if we were looking for something closer to the top of our heap, like we're looking for the number, let's say 80. Well, we start here, and we know that 80 is definitely less than 86. So we have both of these. Well, over here, we know that 80 is less than 85. So it's going to be over here potentially. Over here, we have 77. Well, 77 is not greater than 80, so we can cross off this side of the tree. There is no number greater than 77 over here. So we can make a decision and eliminate some of it, but there's no guarantee every step of the way that that's the case, and it depends on the value that we're looking for. So technically, if you do look it up, I believe the big O for searching is O of n divided by 2 on average, but remember that when we have a constant like that, n divided by 2, n times 2, n times 100, it doesn't matter. We simplify it to big O of n. So as n grows, in general, the amount of time it takes to search also grows just at the same rate as n. So it's linear, O of n. So these are not optimized for searching. But when we're talking about insertion and removal, that's the name of the game with heaps. All right, we have time for a quick recap. So we've spent a lot of time talking about binary heaps, which are a type of tree. Well, technically, a binary heap is a type of a heap. We could have other types of heaps, just like a binary tree is a type of a tree. So we have binary heap, which is a type of a heap, which is a type of a tree. Okay, so they're useful on their own, but also to implement other data structures like priority queues, like we just saw a couple videos ago. They are either, when we're talking about binary heaps, they're either max binary heaps or min binary heaps. And the way that it works, the one rule that governs it, aside from the structure, meaning that each node can have a maximum of 2 children. The other rule in a max binary heap is that every parent is larger than its 2 children. In a min binary heap, every parent is smaller than its 2 children, or however many children it has. We fill them out from left to right, so we don't end up with these unbalanced, wonky, one-sided trees. A heap is always filled out from left to right. It looks like a heap. It's a pyramid of stuff. It's a heap, a pile. And with just a little bit of math, we can pretty easily represent heaps using arrays. So we don't have to make pointers. We don't have to make nodes that point to next, dot next, or left and right, or child, or whatever. We can just store them in an array because the rules that we follow makes it very easy to flatten out or represent just using numerical indices. And so that's a nice, easy way of doing it. You don't have to represent heaps that way. You could do heaps. You could make your own class and make a bunch of nodes like we did for binary search trees. It's just easier to do it this way. All right, so that's binary heaps.